What if we told you the galaxy next door is hiding secrets stranger than anything science fiction could dream up? The Andromeda Galaxy, that shimmering spiral of stars we've gazed at for millennia, isn't just a beautiful neighbor, it's a cosmic vault of mysteries, and its outer reaches are teeming with objects so bizarre, they defy everything we thought we knew. Imagine a place where ancient stellar fossils, rogue black holes, and structures with no clear origin lurk in the darkness, far beyond the galaxy's bright core. This is the Andromeda Halo, a vast, ghostly sphere of gas, dust, and enigmatic objects stretching nearly 2 million light-years into the void. Galactic halos are like the hidden backrooms of the universe, where the rules seem to bend and the ordinary becomes extraordinary. But Andromeda's halo is different. It's richer, weirder, and more unpredictable than our own Milky Ways. Recent observations have uncovered 30 objects orbiting within it that don't fit any known category, some glowing with unexplained energy, others moving in patterns that suggest they're being tugged by invisible forces. What are they? Remnants of cannibalized galaxies, dark matter anomalies, or something even more unsettling? This isn't just a story about distant specks of light. It's a detective tale written across the cosmos, one that challenges our understanding of how galaxies live, grow, and evolve, and you're about to join the investigation. Over the course of this journey, we'll unravel the secrets of these 30 strange objects, each one a clue waiting to be deciphered. By the end, you'll see Andromeda not as a static pinwheel in the sky, but as a dynamic, almost alive entity with a halo that whispers tales of cosmic violence, ancient collisions, and maybe, just maybe, forces we've yet to name. So let's dive into the unknown together, because the universe's greatest stories are always hiding in the shadows. The first of these enigmas drifting through Andromeda's halo isn't just strange, it's practically see-through. Picture a hydrogen cloud so vast it could swallow our entire Milky Way, yet nearly invisible to telescopes, stretching over 160,000 light-years across. This cosmic phantom was only detected when radio telescopes caught the faint whisper of hydrogen atoms vibrating at a specific frequency, like hearing a single note played on a piano in a thunderstorm. So how does something this colossal stay hidden? The answer lies in its ghostly nature. Unlike stars or glowing nebulae, this cloud is cold and diffuse, with atoms so spread out that if you flew through it, you'd never know. But its sheer size betrays its significance. This isn't just leftover gas. Some astronomers believe it's the skeletal remains of a dwarf galaxy torn apart by Andromeda's gravity billions of years ago. Its stars ripped away while its gas lingered like cosmic fog. Others argue it could be primordial fuel, a relic from the galaxy's birth that never ignited into stars. Here's where it gets eerie. The cloud isn't drifting aimlessly. It moves with purpose, orbiting Andromeda in a way that suggests something unseen is guiding it, perhaps dark matter's gravitational hand or the echo of a violent merger. And it's not alone. Similar clouds lurk in the halo, hinting at a hidden history of galactic cannibalism. Every time Andromeda feasted on a smaller neighbor, it may have left behind these ghostly fingerprints. So while we call it a cloud, it's really a crime scene, one that's still telling its story. But the phantom hydrogen cloud isn't the only specter haunting Andromeda's halo. Lurking nearby is something even more elusive, a dense clump of dark matter so massive it bends the fabric of space around it, yet leaves no visible trace. Unlike stars or gas, this entity reveals itself only through its gravitational grip, warping the paths of nearby objects like an invisible hand steering marbles across a table. When astronomers first noticed stars and dwarf galaxies orbiting in odd, skewed patterns, they knew something unseen was pulling the strings. This isn't just any dark matter pocket, it's a cosmic anomaly. According to simulations, dark matter should be smoothly distributed in a galaxy's halo, like flour sifted evenly through a bowl. But this clump defies expectations, knotting itself into a dense, tangled mass that current models struggle to explain. Some theories suggest it could be the remnant of a smaller galaxy whose stars were stripped away, leaving behind its dark matter skeleton. Others propose it's a rare snapshot of dark matter interacting with itself in ways we don't yet understand, a possibility that could rewrite the rules of physics. The real puzzle: this clump isn't behaving like dark matter should. Instead of sitting quietly in the halo's outskirts, it's drifting closer to Andromeda's core, as if tugged by some unseen force. If dark matter is truly cold and non-interactive, as most theories assume, why is it clumping and moving like this? The answer could upend decades of astrophysics, hinting at hidden properties or even entirely new particles. For now, this ghostly knot remains a cosmic question mark, one that reminds us how much of the universe is still written in invisible ink. Now we come to a group of cosmic fugitives, stars racing through Andromeda's halo like they're being chased. This isn't just any star cluster, it's a tight-knit family of hundreds of stars, all moving together at speeds that defy logic. Most star clusters in a galaxy's halo drift lazily, like leaves on a pond, but this one barrels outward as if hurled by some unseen force. The mystery deepens when you trace their path backward. These stars didn't form in the halo, they were violently ejected from Andromeda's bustling disk, flung into the cosmic hinterlands. But what could launch an entire cluster with such force? One leading theory points to Andromeda's supermassive black hole. Imagine a binary star system wandering too close to the black hole's maw. One star gets captured while the other is slingshotted away at incredible speed, dragging its siblings along like a gravitational chain reaction. It's the cosmic equivalent of a pinball machine gone rogue. Yet there's another, even more dramatic possibility: a close encounter with another galaxy. Andromeda's history is written in collisions. It's grown by devouring smaller galaxies, and each merger sends shockwaves through its structure. If a dwarf galaxy plowed through Andromeda's disk at the right angle, the gravitational turbulence could have ripped this cluster loose, sending it careening into the halo like a billiard ball struck by a cue. What makes these orphaned stars truly fascinating is their defiance of expectations. They're not scattered or disrupted by their journey. They've clung together against all odds, a testament to the unbreakable bonds of gravity. Studying them could reveal secrets about the extreme environments near black holes or the chaotic aftermath of galactic mergers, events we can't replicate in simulations but see etched in the trajectories of these runaway stars. One thing's certain: their speed isn't just a fluke. It's a clue pointing to moments of violence hidden in Andromeda's past. Tucked within the vast darkness of Andromeda's halo, a luminous thread weaves through the void like a river of fire, a colossal filament of ionized gas stretching over 25,000 light-years. Unlike the faint hydrogen clouds we've seen before, this structure burns with a ghostly blue glow of energized particles, visible even against the black canvas of intergalactic space. It doesn't just sit there, it writhes as if still alive with the energy of whatever cosmic event birthed it. The filament's origins are as mysterious as its appearance. One prevailing theory ties it to Andromeda's violent past. When galaxies merge, they don't just swap stars, they send shockwaves through their surrounding gas, like ripples from a stone tossed into a pond. These waves can stretch and twist vast reservoirs of hydrogen, heating them until they glow. Picture this as the aftermath of a cosmic car crash, where debris isn't twisted metal but superheated gas, flung outward in ribbons that take billions of years to fade. But there's a twist. The filament isn't just pointing randomly, it aligns eerily with the path of a dwarf galaxy Andromeda likely devoured 2 billion years ago. Like a trail of breadcrumbs leading back to the scene of the crime, it could mark the dying screams of that smaller galaxy's gas, torn apart and set ablaze as it spiraled into oblivion. Yet another possibility is even more dramatic: intergalactic winds. Andromeda isn't floating in isolation. It's moving through the sparse gas of the cosmic web, the universe's vast network of matter. At certain speeds, this movement can create a wind powerful enough to pull streams of gas from the galaxy's disk, stretching them into these eerie, glowing tendrils. If true, the filament isn't just a relic. It's a live wire crackling with the energy of Andromeda plowing through the cosmos. What makes this structure truly captivating is its defiance of expectation. Filaments like these were assumed to be fragile, dissipating quickly after forming. But this one persists, a glowing scar that refuses to fade. Whether it's a tombstone for a dead galaxy or a beacon of Andromeda's journey through space, it's proof that even the emptiest corners of the universe are anything but quiet. Against the sprawling darkness of Andromeda's halo, a glittering time capsule drifts silently, a globular cluster so ancient its stars burn with the pristine light of the early universe. This isn't just another cluster, it's a relic, a celestial fossil with metal levels so shockingly low. It's as if the stars themselves were forged before heavy elements even existed. To grasp why this matters, imagine the universe's first stars. Born from nothing but hydrogen and helium, these pioneers lacked the complex elements we take for granted today. No iron, no silicon, not even traces of carbon. When they died in supernova, they seeded the cosmos with heavier metals, enriching future generations of stars. But this cluster, its stars are like unopened letters from that dawn of time, their composition nearly unchanged for over 13 billion years. What's baffling is its location. Globular clusters typically orbit near galactic cores where star formation is bustling, but this one lingers in the halo's outskirts as if exiled. One explanation is that it didn't form with Andromeda at all. It was stolen. During one of the galaxy's ancient collisions, this cluster may have been wrenched from a smaller, doomed neighbor, left to wander the halo like a cosmic castaway. Yet there's a twist. Its stars aren't just metal poor, they're unusually synchronized in age and composition. Most clusters show some variation, bearing scars of later star formation or mergers. But this group is eerily uniform, suggesting it formed in a single, rapid burst. A snapshot of star birth conditions so pristine, modern galaxies can't replicate them. Studying it is like cracking open a time capsule buried at the universe's birth. The light from these stars carries clues about how the first galaxies assembled, how metals spread through the cosmos, and even how dark matter's gravitational scaffolding shaped early structures. If we could decode their chemical fingerprints, we might finally understand what the universe looked like before everything, before planets, before life, before even the seeds of galaxies like Andromeda took root. This cluster doesn't just defy expectations, it forces us to rethink how galaxies grow. We assumed metal-poor stars were rare in massive spirals like Andromeda, their halos built from digested dwarf galaxies richer in metals. But here they are, living proof that some fragments of the early universe survived, untouched, in plain sight. Every flicker from these ancient stars is a whisper from a time when the cosmos was new, and Andromeda was just a dream in the dark. Hidden in the depths of Andromeda's halo, something monstrous is on the move, a supermassive black hole not anchored to any galaxy, but racing through the void like a cosmic fugitive. This isn't just any black hole, it's a titan with the mass of millions of suns, hurled into the darkness by forces so violent they could reshape an entire galaxy. And it's not alone. Stretching behind it like breadcrumbs in a fairy tale is a trail of orphaned stars, their chaotic orbits painting a picture of sheer cosmic havoc. How does a black hole this size go rogue? The answer lies in Andromeda's violent past. When two galaxies merge, their central black holes eventually collide, spiraling toward each other in a gravitational dance. But if a third black hole enters the mix, the chaos can fling one of them outward at unimaginable speeds, like a slingshot fired by the universe itself. Simulations suggest this might be what happened here, a three-body tango so extreme it ejected the loser into the halo at thousands of kilometers per second. But here's the twist. Unlike smaller stellar mass black holes that vanish into the dark, this supermassive beast can't hide. Its gravity is so immense it drags entire star clusters with it, yanking them from their original orbits and leaving a luminous wake in its path. These stars aren't just following, they're being torn, stretched, and rearranged, their light twisted into strange, elongated streams that glow against the halo's emptiness. What makes this runaway truly eerie is what it implies about Andromeda's core. If a black hole this size was ejected, what's left behind, the merger that spawned it, would have been apocalyptic, shaking the galaxy to its foundations. Some astronomers speculate that Andromeda's current supermassive black hole might actually be the product of that same collision, a monstrous hybrid born from the fusion of its predecessors. Yet the most tantalizing question isn't about where this rogue came from, it's where it's going. A black hole this size, untethered from a galaxy, could plow through star-forming regions like a bulldozer, disrupting gas clouds and triggering or stifling new star birth in its wake. If it ever approaches another galaxy, its gravity could warp the entire structure, leaving scars that last for eons. For now, this cosmic outlaw drifts through the halo, a reminder that even the mightiest objects in the universe aren't immune to chaos. Its very existence challenges our assumptions about how galaxies evolve, proving that sometimes the universe doesn't just build, it throws. Deep in the outer reaches of Andromeda's halo, a ghostly shape flickers at the edge of detection, a dwarf galaxy so faint it barely qualifies as a galaxy at all. Unlike the glittering spirals we're used to, this one is little more than a smudge of light, its stars scattered so thin that if you stood within it, the night sky would appear almost empty. Yet it's real, a fragile relic clinging to existence in a region where most galaxies are torn apart. What keeps such a wispy structure intact? The answer lies in its lack of something rather than its abundance. Most galaxies are rich in dark matter, the invisible glue that holds them together against the tides of gravity. But this phantom dwarf seems to have almost none, making it so lightweight that it slips through the cosmic cracks. Imagine a handful of dry sand tossed into a storm. Most clumps would disintegrate, but a few loose grains might drift unharmed. That's the survival strategy here, too faint to notice, too diffuse to destroy. Yet there's a paradox. Without dark matter's gravitational anchor, this galaxy shouldn't exist at all. Its stars should have scattered into the void long ago, torn apart by Andromeda's gravity or the nudges of passing objects. The fact that it endures suggests something else is at play, perhaps a delicate balance of orbits that keeps its stars just far enough apart to resist collapse, yet close enough to remain a family. What's truly bizarre is how these ghost galaxies form in the first place. One theory suggests they're the stripped cores of once larger galaxies, their outer layers peeled away by tidal forces until only the barest skeleton remains. Another idea posits they're cosmic misfires, regions where gas collected but never quite ignited into robust star formation, leaving behind a failed galaxy that somehow slipped into Andromeda's grip. Then there's the timing. This dwarf stars are ancient, some nearly as old as the universe itself. That means it's been drifting in Andromeda's halo for billions of years, a witness to countless collisions and mergers, events that should have shattered it. Its survival hints at an even deeper mystery. Perhaps the halo isn't the chaotic blender we assume, but a place where certain structures, if they're faint and slow enough, can persist like whispers in a hurricane. Studying this phantom isn't just about adding to the catalogue of weird objects. It challenges our understanding of galaxy formation, dark matter's role, and even the limits of gravitational physics. If something this fragile can endure, what else is hiding in the halos of galaxies, not just in Andromeda, but in the countless others spinning through the dark? Every flicker of light from these ghostly stars is a clue, and the universe is daring us to follow them. Among the faint whispers of Andromeda's halo, an invisible giant makes its presence known, not through light but through a thunderous roar of radio waves. This is the radio bubble, a vast sphere of energetic particles stretching over tens of thousands of light years, pulsing with the echoes of some cataclysmic event buried deep in the galaxy's past. If our eyes could see radio frequencies, this structure would dwarf even Andromeda's luminous disk, a ghostly crown hovering in the darkness. The bubble's origins trace back to two equally dramatic possibilities. The first involves Andromeda's central supermassive black hole. Like all monsters of its kind, it isn't always quiet. There are periods when it feeds voraciously, swallowing gas and stars in a frenzy. When this happens, the black hole doesn't just eat, it retaliates, spewing jets of high-energy particles at near light speed. These jets can inflate colossal bubbles in the surrounding gas, like a blowtorch carving cavities in ice. The bubble we see today might be the fossilized remnant of such an eruption, a relic from an era when Andromeda's core was a raging quasar. But there's another contender for this cosmic disturbance, a starburst so intense it shook the galaxy. Picture a time when Andromeda's disk was a fireworks show of newborn stars, each one exploding in supernova at a rate hundreds of times faster than today. These successive detonations would have pumped the halo full of hot gas and cosmic rays, creating a shockwave that ballooned outward, pushing everything in its path. The bubble could be the aftermath of that stellar frenzy, a scar left by the galaxy's most fertile epoch. What makes this structure so fascinating is how it challenges our assumptions. Andromeda has long been considered a quiet galaxy, no longer birthing stars at a breakneck pace, its black hole mostly dormant. But the radio bubble tells a different story, one of past violence, of energies so extreme they reshaped the halo itself. It's proof that even the calmest-looking galaxies have tempestuous histories hidden just beneath the surface. Then there's the timing. The bubble's size and the speed of its expansion suggest the event that created it occurred roughly 200 million years ago, a blink in cosmic terms. That means Andromeda wasn't always the serene spiral we see today. Not long ago, by galactic standards, it was a place of chaos, its core either erupting or its disk aflame with stellar birth. Even more intriguing, the bubble isn't alone. Similar structures have been spotted in other galaxies, but Andromeda's is uniquely crisp, its edges sharp against the halo's emptiness. This clarity suggests the bubble is still expanding, its energy not yet diluted by the surrounding void. By studying its motion, astronomers can essentially rewind the tape, reconstructing the exact conditions that birthed it. Perhaps the most tantalizing question isn't about the past but the future. If Andromeda's black hole or star formation can awaken once, it could happen again. The bubble is a reminder that galaxies aren't static museums of stars. They're living, breathing entities capable of sudden and violent transformation. And if our own Milky Way is headed for a collision with Andromeda in a few billion years, understanding these outbursts isn't just academic, it's a preview of the cosmic fireworks to come. Winding through Andromeda's halo like a luminous river lost in the dark, an ethereal band of stars stretches farther than the eye can comprehend. A stellar stream, the scattered remains of a galaxy torn apart and digested. This isn't a random scattering of stars, it's a cosmic crime scene, a trail of celestial breadcrumbs revealing a brutal feast that unfolded over billions of years. The stream's stars move in eerie unison, their orbits tracing the same path as if still bound by the memory of their original home, a dwarf galaxy long since devoured. Reconstructing this galactic murder relies on the forensic power of simulations. Imagine a small galaxy, perhaps 1,000 times less massive than Andromeda, drifting too close. As it enters the halo, the larger galaxy's tidal forces, the difference in gravity between the near and far sides, begin stretching it like taffy. Over countless orbits, the dwarf stars are peeled away, first in delicate tendrils, then in great arcing ribbons, until all that's left is this glittering filament, a shadow of what once was. The process isn't quick, it's a slow-motion disintegration, a gravitational ballet where the victim's remains are woven into the predator's halo. But this stream isn't just a relic, it's a time machine. The star's chemical fingerprints tell us the original galaxy was poor in heavy elements, a sign it formed early in the universe, untouched by the enrichment of later supernova. Their ages cluster around 12 billion years, making them some of the oldest witnesses to Andromeda's growth, and their paths they're a puzzle. Unlike the neat, predictable orbits of stars born in the halo, these stars move with a subtle wobble, their trajectories subtly warped by dark matter clumps we can't see, a hidden architecture of gravity sculpting the stream like an invisible hand. The most striking detail lies in the stream's gaps. Simulations show these voids aren't random. They're wounds from later encounters, moments when passing dwarf galaxies or dark matter substructure punched through the stream, disrupting its flow. It's as if the river of stars remembers every cosmic ripple, its imperfections mapping the halo's turbulent history. Some gaps even align with known satellite galaxies, implicating them as accomplices in this celestial tug of war. What makes this stream extraordinary isn't just its origin, it's its future. Unlike the chaotic orbits of stars in a cannibalized galaxy's core, stream stars follow predictable paths, making them perfect tracers for the halo's gravitational field. By studying their slightest deviations, astronomers can weigh Andromeda's dark matter, not just in bulk, but in fine detail, revealing where it clumps, where it's sparse, and how it shapes the galaxy's invisible skeleton. This ghostly ribbon of stars is more than debris. It's a testament to the dynamic, ever-changing nature of galaxies. Andromeda didn't grow by magic. It grew by conquest, swallowing smaller neighbors and weaving their stars into its own tapestry. The stream is a living record of that hunger, a reminder that even the grandest spirals are built piece by piece from the remnants of the cosmic past. Buried in the silent expanse of Andromeda's halo, a pinpoint of energy pulses with relentless intensity, an X-ray source so bright it outshines entire star clusters, yet vanishes when astronomers train optical telescopes on its location. There's no visible star, no glowing gas cloud, just an eerie beacon of high-energy radiation flickering against the darkness like a cosmic strobe light. This isn't just a mystery, it's a celestial riddle wrapped in invisible fire. The sheer power of this X-ray emission narrows down the suspects. Ordinary stars, even the hottest ones, can't produce such energetic light. The culprit must be something extreme, a neutron star spinning at dizzying speeds, its magnetic field whipping particles to near light speed, or a black hole devouring gas in a silent frenzy. But here's the twist, neither explanation fits perfectly. If it were a neutron star, we'd expect pulses of radio waves accompanying the X-rays, a telltale signature of these cosmic lighthouses. Yet the silence is deafening, and while black holes often glow in X-rays as they feast, this source flickers unpredictably, flaring and dimming with no discernible pattern, unlike the steady glow of most accretion disks. Then there's the location. This object drifts far from Andromeda's star-rich disk, isolated in the halo's emptiness. Most X-ray binaries pairs where a compact object like a black hole siphons material from a companion star live in crowded galactic neighborhoods. How did this one end up so alone? One possibility is a cosmic ejection. A violent supernova explosion could have kicked the system out of Andromeda's disk, sending it careening into the halo like a bullet fired into the void. Another theory suggests it's the remnant of a long-dead dwarf galaxy, its stars scattered but its densest object left behind, still burning with stolen energy. But the most tantalizing explanation lies in the realm of the unknown. Some astronomers speculate this could be a rare intermediate mass black hole, a missing link between the stellar mass black holes born from dying stars and the supermassive giants anchoring galactic centers. These elusive middles are thought to lurk in halos, relics of the universe's chaotic youth when mergers built galaxies piece by piece. If confirmed, this X-ray source wouldn't just be a curiosity. It'd be a living fossil, a clue to how black holes grow and galaxies assemble over eons. What makes this object truly unsettling is its defiance of neat categorization. It's too bright for a neutron star, too erratic for a typical black hole, and too isolated for standard models. Every observation seems to deepen the mystery rather than solve it. Perhaps the answer lies in something we've never seen before. A black hole with an unconventional diet, a neutron star cloaked in exotic physics, or even an entirely new class of celestial object waiting to be named. For now, the X-ray source keeps its secrets pulsing in the dark like a coded message from the universe. Each flicker carries data, a whisper of processes we don't yet understand. And that's the thrill of the hunt. In the halo's shadowy depths, the most ordinary-looking patch of sky might hide the extraordinary. All we have to do is keep listening. High above Andromeda's glittering disk, a cosmic carousel of debris spins against the grain, a rogue belt of stars, gas, and dust orbiting at a near-perpendicular angle to the galaxy's main plane. This isn't just a random scattering of leftovers. It's the ghostly imprint of a polar ring, a rare galactic structure that forms when two galaxies collide not just once but twice in a dizzying gravitational dance. Picture this: a smaller galaxy, maybe a tenth of Andromeda's size, approaches at a sharp angle. On its first pass, it's stripped of stars and gas, but its trajectory carries it back around in a long, looping orbit. By the time it returns, its remains have been stretched into a vast ring, circling the larger galaxy like a belt around a waist. This isn't a gentle merger. It's a cosmic slingshot that leaves behind a debris field spinning at right angles to everything else. What makes polar rings so extraordinary is how they defy galactic norms. Most galaxies settle into orderly disks, with stars and gas orbiting in a single, flat plane. Think of a vinyl record spinning on a turntable. But a polar ring breaks all the rules, wrapping around the galaxy's poles like a carnival ride gone rogue. In Andromeda's case, the remnants of this collision aren't just a curiosity, they're a time capsule. The debris' motion, composition, and even its scars reveal details about the long-dead galaxy that created it, how massive it was, how fast it moved, even the angle at which it struck. Then there's the halo's role. Normally, a galaxy's halo is a chaotic place where orbits are scrambled and structures erased over time. Yet this polar debris has survived, its stars clinging to their unnatural path for billions of years. That resilience hints at something unexpected. The halo isn't just a dumping ground for galactic wreckage. It's a dynamic archive, preserving some structures while erasing others, as if the universe itself chooses which memories to keep. The real kicker: polar rings aren't just relics, they're active shapers of their galaxies. The debris' gravity tugs on Andromeda's disk, warping its outer edges and funneling gas into strange off-kilter streams. Some models suggest these collisions might even spark bursts of star formation, as the misaligned debris slams into the galaxy's gas clouds like a mallet striking a gong. But here's the twist: polar rings are vanishingly rare. Only about 1 in every 1,000 galaxies shows evidence of this kind of collision. That makes Andromeda's debris not just a scientific curiosity, but a cosmic lottery ticket, a glimpse into one of the most violent, improbable events a galaxy can experience. And it's all floating right there, written in the stars above Andromeda's poles, waiting to be read. Streaking through the emptiness of Andromeda's halo like a bullet through smoke, a lone star defies all expectations, blazing outward at speed so extreme, not even the galaxy's gravity can hold it. This isn't just a fast-moving object, It's a hypervelocity star, a cosmic runaway hurtling at over 1 million miles per hour, fast enough to cross the distance between Earth and the Moon in less than 15 minutes. And its trajectory spells a dramatic fate. Unless something intervenes, it will become the first known star to escape Andromeda entirely, flung into the intergalactic void with no way home. What force could launch a star with such violence? The leading culprit is Andromeda's supermassive black hole. Picture a binary star system, two stars locked in orbit, wandering too close to the black hole's event horizon. As tidal forces wrench them apart, one star gets captured, spiraling inward to its doom, while the other is catapulted outward at a significant fraction of light speed, like a stone from a sling. The energy required is almost unimaginable, equivalent to detonating 1 million nuclear bombs simultaneously. But for a black hole with the mass of 100 million suns, it's just another day at the office. Yet there's another, equally explosive possibility, a supernova kick. When certain massive stars die, their cores collapse asymmetrically, triggering a detonation so lopsided it can send the remnant, a neutron star or black hole, rocketing through space like a cannonball. If this hypervelocity star was once part of such a system, the supernova's shockwave could have blasted it free, turning its companion's death into an accidental launch sequence. The real mystery lies in the star's composition. Most hypervelocity stars flung from galactic centers are young, hot, and massive stellar giants with short lifespans. But this one is older, cooler, and surprisingly modest in size, raising questions about how it gained such speed. Perhaps it was part of a densely packed cluster, where gravitational interactions between stars acted like pinballs, accelerating it gradually until it reached escape velocity. Or maybe it hitchhiked on a rogue intermediate mass black hole, using the object's gravity as a cosmic catapult before being cast adrift. What makes this star's journey so remarkable isn't just its speed, it's the loneliness ahead. As it leaves Andromeda's halo, it will enter a realm where galaxies are mere pinpricks in the distance, where the space between stars stretches for millions of light years. Unlike most stellar runaways, which eventually slow and settle in a galaxy's outer fringes, this one is destined to become a true wanderer, adrift in the abyss between galactic superclusters. Yet even in exile, it carries clues. The star's light contains chemical fingerprints that reveal its birthplace, not in Andromeda's bustling disk, but in one of the small satellite galaxies absorbed long ago. Its speed and trajectory map the gravitational forces at play during that ancient merger, offering a rare glimpse into the chaotic processes that built Andromeda's halo. And if other hypervelocity stars follow similar paths, they could trace invisible currents of dark matter, revealing the hidden architecture of the galaxy's gravitational field. This stellar fugitive is more than a curiosity, it's a testament to the universe's capacity for both violence and beauty. In its defiance of gravity, we see the aftermath of cosmic cataclysms, the echoes of black holes feeding and stars exploding. And in its journey, we're reminded that even in a galaxy of 400 billion stars, no two paths are the same. Some stars burn quietly where they're born. Others are destined to run. Nestled within Andromeda's halo, a cluster of stars glows faintly, too faintly for its sheer gravitational pull. This is no ordinary star group, it's a cosmic paradox, a gathering where the numbers don't add up. Based on its visible light, the cluster should weigh modestly, but its gravity tells a different story. It tugs on surrounding objects with the strength of something far more massive, as if hiding a secret beneath its shimmering surface. The discrepancy lies in what astronomers call the mass-to-light ratio, a measure of how much gravity an object exerts compared to how bright it appears. For most star clusters, this ratio is predictable. Stars contribute both light and mass in roughly equal proportions. But here, the math breaks down. This cluster's gravity suggests it's at least 10 times heavier than its luminosity can explain, leaving scientists with two haunting possibilities. Either it's riddled with dark matter, an invisible scaffold binding the stars together, or it conceals a swarm of black holes lurking unseen among its glittering members. Dark matter in a star cluster would be bizarre, as these structures typically form in regions where dark matter is sparse. Most clusters are born in galactic disks, where stellar interactions strip away dark matter early on. But if this one formed differently, perhaps in the halo itself, or as the remnant of a devoured dwarf galaxy, it might have retained its dark matter cocoon, like a fossil preserved in amber. Then there's the black hole scenario. Imagine dozens, even hundreds of stellar mass black holes, the remnants of massive stars that collapsed nestled between the cluster's visible stars. Their combined gravity would explain the extra mass, but their darkness would render them nearly invisible. Such a dense population of black holes isn't just rare, it's unprecedented. Normally, black holes either sink to a cluster's core or get ejected by gravitational interactions. For so many to persist would require a delicate balance, as if the cluster were a cosmic mousetrap, ensnaring them before they could escape. The strangest clue comes from the cluster's motion. Unlike typical globular clusters which orbit galaxies in predictable ellipses, this one moves with a strange, almost meandering path, as if jerked around by unseen hands. Some researchers speculate that dark matter clumps, or the gravitational wakes of hidden black holes, could be tugging it off course, warping its trajectory in ways that mirror the dance of invisible partners. What's at stake isn't just solving a celestial math problem. If dark matter truly resides here, it challenges our understanding of how star clusters form and evolve. If it's black holes, we might be staring at a graveyard of ancient stellar giants, their corpses clustered like relics of a forgotten era. Either answer rewrites the rules, proving that even the smallest corners of Andromeda's halo hold universe-shaking secrets. The cluster's dim glow isn't a sign of insignificance, it's a beacon, illuminating how much we still have left to discover. Scattered like lost travelers across the vastness of Andromeda's halo, some stars don't just look ancient, they feel it. These aren't merely old, they're cosmic elders, survivors from an era when the galaxy itself was little more than a swirling cloud of primordial gas. Their light carries the unmistakable signature of extreme metal poverty, meaning they formed before supernova had a chance to pepper the universe with heavier elements. To find them is to stumble upon the galaxy's first bricks, the foundational pieces Andromeda used to build itself. What makes these stellar fossils extraordinary isn't just their age, it's where they're found. Unlike the orderly populations of stars in Andromeda's disk, these relics drift in chaotic orbits, as if they were tossed into the halo by some long-ago turmoil. Their paths trace back to the galaxy's most violent chapters, when dozens of smaller protogalaxies, each a clump of gas and early stars, collided and merged over billions of years. Picture a crowded construction site where workers from different crews toss their tools into a shared pile. These stars are the leftover hammers and nails, still bearing the marks of their original owners. But there's a twist hidden in their chemistry. While most halo stars in our Milky Way share similar metal-poor compositions, Andromeda's fossil stars show startling diversity. Some are nearly pure hydrogen and helium, as expected from the universe's infancy, while others contain faint traces of heavier elements, just enough to hint at a single generation of prior stars. This suggests Andromeda didn't grow through neat, uniform mergers, but through a messy buffet of cosmic digestion, gobbling up building blocks of varying ages and histories. Some protogalaxies may have birthed a few stars before being swallowed, while others were consumed before they could ignite even one. The most telling clue lies in their distribution. These ancient stars aren't spread evenly through the halo. They cluster in distinct streams and clumps, like crumbs marking the paths of long-vanished dwarf galaxies. By mapping their positions, astronomers can reconstruct Andromeda's growth spurt by spurt, identifying which stellar groups came from which mergers. One particularly dense knot might be the ghostly core of a galaxy 10 times smaller than Andromeda, ripped apart but never fully digested. Another sparse arc could be the stretched remains of a cosmic minnow, devoured so early that its stars had barely begun to shine. Then comes the real surprise: some of these fossil stars are younger than they should be. Normally, metal-poor stars are assumed to be ancient, but a few in Andromeda's halo burn hotter and brighter than their chemistry suggests, as if they formed late from gas that had somehow avoided contamination. One theory proposes they were born in ultra-faint dwarf galaxies that lingered in isolation for billions of years, only merging with Andromeda recently. Another suggests they're the product of cold flows, filaments of pristine gas that continued raining onto galaxies long after the early universe's chaos subsided, providing fresh material for oddly old-looking stars. Studying these stellar time capsules does more than satisfy curiosity. It reshapes our understanding of galaxy assembly. Andromeda's fossil halo implies its growth was prolonged and complex, a series of feasts rather than a single growth spurt. Some stars may have arrived late, others early, with each wave leaving its chemical fingerprint on the galaxy's evolving identity. That diversity makes Andromeda a Rosetta Stone for galactic archaeology, offering clues not just about its own past, but about how all massive spirals emerge from the dark. Perhaps the most humbling realization is that these stars were here long before Andromeda took its current shape, before Earth existed, before the Sun ignited, even before the Milky Way's spiral arms finished twisting into place. They've watched the galaxy evolve from a chaotic infant into the majestic spiral we see today, silent witnesses to eons of cosmic drama. And they'll still be here long after our own star fades, drifting through the halo like living monuments to the universe's relentless creativity. Deep within Andromeda's halo, an invisible glow pulses with the energy of the universe's most violent processes, not in visible light, but in gamma rays, the highest energy radiation known. This vast, diffuse emission stretches across thousands of light-years, a faint shimmer detectable only by the most sensitive space telescopes. Unlike the pinpoint flashes of gamma-ray bursts, this glow is omnipresent, like a cosmic fog of high-energy particles saturating the halo's darkness. And its origin, that's where the mystery deepens. One leading explanation points to dark matter's shadowy realm. Theoretical models suggest that when dark matter particles collide, they might annihilate each other in bursts of energy, producing gamma rays as a byproduct. If true, this glow could be the first tangible evidence of dark matter's invisible interactions, a smoking gun for physicists who have spent decades searching for proof. The halo's outer reaches, where dark matter is thought to cluster most densely, would be the perfect hunting ground for such signals, yet there's a compelling counterargument: cosmic rays. These high-energy particles, accelerated by supernova explosions or Andromeda's magnetic fields, could be slamming into hydrogen atoms in the halo, creating gamma rays as they collide. The Milky Way produces similar emissions, though on a smaller scale, suggesting this might be a natural byproduct of galactic physics rather than dark matter's signature. The challenge lies in the patterns. Cosmic ray-induced gamma rays tend to follow the distribution of gas, while dark matter annihilation would correlate with gravitational models of the halo's mass. So far, the glow aligns ambiguously with both. Intriguingly, the debate doesn't end there. Some researchers propose a third option: a population of ancient pulsars, the spinning cores of dead stars, too dim to see individually but collectively flooding the halo with gamma rays. Others suggest the glow could be fallout from Andromeda's past mergers, stellar remnants, and rogue black holes heating the halo's gas to extreme temperatures. Each theory leaves its own fingerprint in the gamma-ray spectrum, subtle variations in energy that telescopes are only now learning to decode. What makes this enigma so electrifying is its potential to rewrite physics. If dark matter is truly behind the glow, we're glimpsing a fundamental particle that makes up 27% of the universe, a discovery that would rival the Higgs boson in significance. If cosmic rays are the culprit, it forces us to rethink how energy propagates through galactic halos, transforming them from quiet backwaters into particle accelerators of unimaginable scale. And if it's something else entirely, that's the thrill of the hunt. The gamma-ray glow isn't just a puzzle, it's a mirror held up to our ignorance, reflecting how much we still have left to learn about the hidden engines driving the cosmos. For now, the glow keeps its secrets, bathing Andromeda's halo in silent, high-energy light. Every new observation sharpens the picture, peeling back layers of possibility. Whether it's dark matter's whisper, cosmic rays roar, or something beyond our current theories, one thing is certain. In the grand tapestry of the universe, even the faintest light can illuminate the darkest mysteries. In the swirling debris of Andromeda's halo, a cosmic phoenix rises, not a relic from the early universe, but something entirely unexpected. A brand new dwarf galaxy taking shape before our eyes. This isn't some ancient fragment surviving from the cosmos's infancy. It's a tidal dwarf galaxy, a vibrant stellar nursery born from the wreckage of galactic collisions. Picture two galaxies grazing each other in a gravitational dance, their gas and stars torn loose in great luminous streams. Most of that debris scatters into the void, but sometimes, just sometimes, the chaos conspires to create rather than destroy. What sets this dwarf apart is its defiance of convention. Classic dwarf galaxies are thought to be primordial, tiny, ancient clumps of stars and dark matter left over from the universe's first billion years. But this one, it's a cosmic upstart forged from material ripped free during Andromeda's past mergers. Its stars aren't old and metal poor, they're young, blue, and bursting with life, their chemistry rich with the heavier elements cast off by generations of supernova. The galaxy's very existence blurs the line between destruction and creation, proving that even in the aftermath of violence, the universe finds ways to rebuild. The real marvel lies in its star-forming regions. Unlike the sleepy, aging stars of most halo dwarfs, this one crackles with activity. Dense knots of gas collapse under their own gravity, igniting clusters of newborn stars so bright they outshine the rest of the dwarf combined. These aren't the feeble flickers of an aging cosmos, they're full-throated roars of stellar birth, each one a testament to the resilience of matter. Some of these nurseries are so prolific, they rival the star-forming hubs of Andromeda's main disk, a feat unheard of in the halo's sparse outskirts. Yet the tidal dwarf's origins are written in its orbit. Unlike primordial dwarfs which move on wide, looping paths, this newcomer traces a tighter, more erratic route, a fingerprint of the violent encounter that birthed it. Simulations suggest it likely formed from the wreckage of a collision between Andromeda and a mid-sized galaxy over 2 billion years ago. As the two galaxies wrestled, their gravitational forces stretched and twisted vast clouds of gas, some of which broke free only to coalesce into this improbable new entity. Here's where it gets even stranger. This dwarf may not be alone. Faint stellar streams nearby suggest other fragments from the same collision, some perhaps still coalescing into new structures. It's as if Andromeda's halo is a cosmic workshop, where debris isn't just scattered but occasionally reassembled into something new. The implications are profound. If tidal dwarfs are common, they could rewrite our understanding of how galaxies grow, not just by swallowing others but by recycling their remains into fresh stellar communities. What makes this object truly revolutionary is its defiance of hierarchy. In the traditional view, big galaxies dominate, consuming smaller ones without a second thought. But tidal dwarfs flip that script. They're proof that even in destruction, smaller galaxies can emerge, not as leftovers but as something entirely new. They're the universe's way of turning chaos into opportunity, reminding us that in the grand tapestry of the cosmos, endings are often just beginnings in disguise. Floating in the depths of Andromeda's halo, two brilliant beacons burn side by side, a pair of quasars so close they appear locked in a cosmic waltz. These aren't just any active galactic cores, they're a binary quasar system, a phenomenon so rare that spotting one in our neighboring galaxy feels like winning the astronomical lottery. Each quasar blazes with the intensity of 1 trillion suns, powered by supermassive black holes gorging on gas at a ferocious rate. But their true significance lies not just in their luminosity, but in their dance. Their movements reveal the violent, messy process of galaxies colliding and merging on a scale we rarely witness up close. The odds of finding such a pair are vanishingly slim. Quasars typically ignite when galaxies are young and gas-rich, their black holes feasting during periods of chaotic growth. By the time galaxies settle into middle age, these brilliant flares usually fade. For two quasars to remain active simultaneously and close enough to orbit one another requires a perfect storm of conditions. Both black holes must be massive enough to sustain accretion disks, both must have a steady supply of gas to fuel their glow, and both must have avoided merging long enough for us to catch them in this fleeting moment. It's like finding two fireflies circling each other in a hurricane. Their presence in Andromeda's halo tells a dramatic story. Most quasars dwell in galactic cores, but these two float far from Andromeda's center, suggesting they're the hearts of smaller galaxies caught in the act of being devoured. As their host galaxies spiral toward oblivion, their black holes each millions of times the mass of our sun are dragged along, lighting up as tidal forces funnel gas into their maws. The quasar's proximity hints at the final stages of this cosmic meal. Their host galaxies have likely been stretched into streams, leaving behind only their brightest, most resilient components. What makes this binary duo invaluable is the window they provide into black hole dynamics. When two supermassive black holes orbit this closely, they warp space-time around them, creating ripples that could one day be detected as gravitational waves. Their interactions also trigger bizarre phenomena. Gas swirling between them heats to millions of degrees, producing X-ray jets that twist like braided ropes, while their competing gravitational pulls shred nearby stars into luminous tidal flares. By studying their light curves and orbital decay, astronomers can test Einstein's theories under extreme conditions, probing how black holes behave when pushed to their limits. Yet the most tantalizing question is what happens next. Binary quasars are thought to be precursors to black hole mergers, the most energetic events in the universe after the Big Bang. If these two continue spiraling inward, they'll eventually collide in a cataclysm that momentarily outshines every star in Andromeda combined. The impact would send gravitational tremors across the cosmos, a space-time shockwave carrying secrets about how black holes grow and galaxies evolve. Whether that merger happens in 1 million years or 1 billion, their current snapshot offers something equally precious, a living textbook on the forces that shape galactic halos written in the fiery script of quasar light. This pair isn't just a curiosity, it's a stopwatch ticking down to an inevitable explosion, a laboratory for physics we can't replicate, and a reminder that even in the vast quiet of a galactic halo, the universe is always writing its next epic. Hidden in the darkness of Andromeda's halo, a spectral shape glows with heat alone, a cosmic ghost visible only to infrared eyes. This mysterious object emits no starlight, no radio waves, nothing but a faint whisper of thermal radiation, as if the universe itself forgot to turn off the heat beneath its invisible shroud. What makes this infrared phantom so baffling isn't just its stealth, it's the sheer impossibility of placing it neatly into any known category. It could be the cooling corpse of a supernova that erupted millennia ago, its once blazing debris now faded to embers. Or perhaps it's an entire galaxy cloaked in dust, so thickly veiled that not a single visible photon escapes its clutches. The evidence tilts toward the stellar corpse theory. When massive stars die in supernova explosions, they leave behind neutron stars or black holes. But first, their ejected material forms a glowing shell called a supernova remnant. Over tens of thousands of years, these remnants expand and cool, fading from visible light into the infrared. The ghost's temperature matches predictions for a remnant in this late stage, its once roaring energies now reduced to a dull cosmic simmer. Yet there's a catch: it's oddly isolated. Most supernova remnants linger near star-forming regions where massive stars are born and die. This one drifts alone in the halo's emptiness, far from the stellar nurseries that should have birthed it. That's where the dusty galaxy theory gains traction. Some galaxies, especially those forming stars at furious rates, become so choked with dust that virtually all their visible light is absorbed and re-radiated as infrared. These ultraluminous infrared galaxies are rare in the local universe but more common in the distant early cosmos. If Andromeda's infrared ghost is one such object, it might be a cosmic hitchhiker, a dwarf galaxy dragged into the halo during an ancient merger, its star formation so frenzied that it shrouded itself in its own smoky exhaust. But here's the twist: the object's infrared signature doesn't perfectly fit either mold. Its spectrum lacks the chemical fingerprints of a supernova remnant, like the telltale lines of ionized oxygen or sulfur. Yet it's also too compact to be a typical dust-obscured galaxy, with a size more akin to a stellar-scale object than a galactic one. This leaves astronomers with a tantalizing third option, something entirely unexpected. Could it be a rogue planetary nebula, the dying breath of a star too small to go supernova, inflated to unusual size by the halo's sparse environment? Or a chance alignment of two unrelated infrared sources, mimicking a single enigmatic entity? The most compelling clue lies in its motion. The ghost isn't stationary, it's drifting through the halo at a speed that suggests it didn't originate there. Tracing its path backward leads astronomers toward Andromeda's disk, hinting it might have been ejected during a violent event, like a close encounter with a black hole or the gravitational slingshot of a passing star cluster. If true, its infrared glow isn't just a curiosity, it's a tracer bullet marking a trajectory of ancient chaos. What makes this ghostly glow so fascinating isn't just the mystery of its identity. It's the reminder that even in an era of advanced telescopes, the universe still hides objects that defy classification. Whether it's a cooling remnant, a hidden galaxy, or something no theorist has yet dreamed up, its infrared whisper challenges us to look deeper, to question assumptions, and to remember that the cosmos always keeps a few secrets in reserve. Every flicker of heat from this enigmatic object carries a story, one that could rewrite our understanding of stellar deaths, galactic evolution, or the hidden populations lurking in plain sight. Until we peer closer, it remains a cosmic question mark, a faint, warm signature in the dark, waiting for its meaning to be uncovered. Looming in the halo's depths like a cosmic mirage, a galaxy the size of the Milky Way hangs suspended, yet it's so faint you could stare right through it. This is no sparse star cluster, but an ultra-diffuse galaxy, a sprawling island of darkness where stars are so few and far between. The entire structure emits less light than a single globular cluster. Imagine a metropolis with the footprint of New York City, but only a dozen street lamps flickering in the void. That's the eerie reality of this galactic ghost. What defies logic isn't just its transparency, but its survival. Galaxies this large should have collapsed under their own gravity long ago, condensing into denser spirals or ellipticals. Instead, this one persists as a wispy giant, its stars drifting apart like smoke in a breeze. The answer may lie in its extreme lack of dark matter, the invisible scaffolding that typically holds galaxies together. Most ultra-diffuse galaxies are found orbiting larger hosts, suggesting they've been stripped of both stars and dark matter by tidal forces, stretched over billions of years until they're little more than stellar cobwebs. Yet Andromeda's specimen throws a wrench in that theory. Unlike most ultra-diffuse galaxies which cluster near massive companions, this one floats in relative isolation, untethered to any obvious gravitational anchor. That raises a radical possibility. It might have formed this way, a galactic misfire where gas spread too thin to ignite robust star formation. Picture a cloud of primordial hydrogen drifting through the early universe, too warm to collapse into dense knots, its potential forever unrealized. Over eons, the handful of stars that did manage to form were left adrift in a sea of near emptiness. The real enigma lies in its invisible residence. Despite its lack of visible matter, the galaxy's stars move faster than gravity should allow, hinting at hidden mass. Some astronomers propose it's rich in dark matter after all, just distributed in an unconventional halo, diffused like the stars themselves. Others suggest alternative physics, like modified gravity, might explain its structure without invoking dark matter at all. What makes this ghostly giant invaluable is its challenge to galactic archetypes. It proves size and luminosity aren't always linked, that the universe can craft galaxies wearing the costume of giants but built like phantoms. Whether it's a stripped relic, a failed construct, or something entirely new, its existence reminds us that even the quietest corners of the cosmos guard transformative secrets. Every flicker from its lonely stars is a verse in a story we're only beginning to read. Stretching across a silent expanse of Andromeda's halo, an invisible force twists the fabric of space itself, not gravity, but magnetism gone wild. This vast region crackles with magnetic fields so contorted, they resemble a cosmic ball of yarn after a cat's playtime, their lines tangled into knots that defy conventional models. Unlike the orderly fields threading through most galaxies, these loops and walls spiral chaotically, as if the universe itself lost its compass here. The Anomalies' origins likely stem from violence on an unimaginable scale. When massive stars die in supernova, their explosions don't just scatter elements, they blast shockwaves through surrounding magnetic fields, twisting them into pretzel shapes. Multiply that by thousands of stellar explosions over millions of years, and you get a magnetic labyrinth, its pathways scrambled beyond recognition. But there's another, even more dramatic sculptor at work: black hole jets. If Andromeda's supermassive black hole ever launched plasma jets into the halo, their torrents could have combed the magnetic fields into bizarre configurations, like a cosmic artist dragging a comb through wet paint. The result, a zone where magnetism doesn't guide, it confuses. This chaos has real consequences for cosmic rays, high-energy particles racing across the universe at near light speed. Normally, magnetic fields steer these particles, funneling them along predictable paths. But here, the field's tangles act like a hall of mirrors, scattering cosmic rays in all directions. Some might bounce back toward Andromeda's disk, others flung deeper into the void. It's a natural particle accelerator gone rogue, where rays gain or lose energy unpredictably, their journeys randomized by the magnetic maze. The oddest part, the Anomalies' edges are sharper than they should be. Magnetic fields usually diffuse gradually, but this one ends abruptly, as if sliced by an invisible knife. Some researchers speculate dark matter could be the culprit. Its gravitational influence might be pinning the fields in place, creating a magnetic fence in the halo. Others suggest we're seeing the aftermath of a collision between two field systems, their forces compressing into a standing wave of distortion. For astronomers, this twisted magnetic tapestry isn't just a curiosity, it's a challenge to fundamental assumptions. Galactic magnetic fields were thought to be relatively uniform at large scales, woven into smooth patterns by eons of evolution. Yet here's proof they can knot themselves into cosmic snarls, their behavior more unpredictable than we imagined. Every wayward cosmic ray spiraling through this zone carries data, a clue to how energy and matter interact in the universe's most extreme environments. What makes this magnetic puzzle truly captivating is its invisibility. unlike glowing gas or sparkling stars, it reveals itself only through its effects, a reminder that some of the cosmos's deepest mysteries don't shine. They pull, they bend, they tangle, and in their silent complexity, they force us to rethink the unseen forces shaping everything we observe. Among the ancient stars drifting through Andromeda's halo, a celestial paradox shines bright, a swarm of stars that look startlingly out of place. These aren't the expected faint, reddened elders of the halo. They're blue stragglers, stellar anomalies burning hotter, brighter, and bluer than their surroundings, as if they've somehow cheated cosmic time. Their very existence defies expectations, like finding a group of teenagers at a retirement home, bursting with energy among the elderly. The mystery lies in their impossible youth. Stars in galactic halos are typically ancient, formed billions of years ago from the pristine gas of the early universe. They should have aged into cool, dim embers by now. Yet blue stragglers blaze with the vigor of stars half their age, their surfaces scorching hot and their light tinged with the unmistakable hue of youth. The secret to their rebirth: cosmic alchemy, stellar collisions or mergers that reignite their fading fires. Picture two aging stars locked in a tight binary dance. Over eons, their orbits decay until gravity pulls them together in a cataclysmic embrace. The resulting merger mixes their hydrogen fuel, creating a single, rejuvenated star with a fresh supply of nuclear energy, a stellar phoenix rising from its own ashes. Alternatively, imagine stars in a densely packed cluster colliding head-on, their outer layers torn away in the impact while their cores fuse into something hotter and brighter. These violent encounters don't just extend the stars' lives, they reset the clock entirely, leaving behind objects that glow with borrowed time. The evidence for this stellar resurrection is etched in their light. Blue stragglers often show unusual chemical signatures, mixes of elements that suggest their outer layers were stripped away or scrambled during their rebirth. Some rotate unnaturally fast, a telltale sign of the angular momentum injected during a merger or collision, like a figure skater pulling in their arms to spin faster. Others pulsate with rhythms that betray their turbulent origins, their interiors still settling from the trauma that reshaped them, but the real intrigue lies in where they're found. Unlike most halo stars, which drift in solitude, blue stragglers often cluster together, as if the conditions that birthed them were localized, perhaps within ancient globular clusters later torn apart by Andromeda's tides. These swarms might be the survivors of stellar demolition derbies, the lucky few that emerged from the chaos brighter than before. Their group dynamics offer clues too. The denser the swarm, the more frequent the collisions, suggesting regions where stars once packed together like commuters in a cosmic subway. What makes these stars more than just celestial oddities is what they reveal about the halo's hidden violence. We often picture galactic halos as serene backwaters, where stars age quietly and nothing much changes. But blue stragglers tell a different story, one of close calls, near misses, and dramatic rebirths. They're proof that even in the darkest, quietest corners of a galaxy, stars can still rewrite their fates. Their glow is a beacon, illuminating not just their own strange histories, but the invisible currents of gravity and chance that shape all stellar lives. Whether born from mergers, collisions, or some other process we've yet to uncover, they challenge our assumptions about how stars evolve and remind us that in the universe, second chances aren't just possible. They shine. Deep in the cosmic shadows of Andromeda's halo, an invisible predator might be lurking, a star that doesn't shine. This isn't a dead husk like a neutron star or black hole, but something far stranger, a theoretical dark star, a celestial phantom built not from ordinary matter, but from exotic particles that refuse to interact with light. Picture a sphere with the mass of a sun, perhaps even 100 suns, drifting unseen through the darkness, its presence betrayed only by the faintest gravitational whisper. The hunt for such objects isn't science fiction, it's a serious frontier in astrophysics. Dark stars, if they exist, could be made of hypothetical particles like actions or neutralinos, leftovers from the universe's earliest moments that clumped together under gravity but never ignited into nuclear fusion. Without the fiery processes that power normal stars, they'd emit no light, no heat, no radio waves, just the subtle tug of their mass-warping space-time around them. Why would Andromeda's halo be the perfect hiding place? Halos are already known to be dominated by dark matter, that mysterious substance making up 27% of the universe. If dark stars form where dark matter clusters most densely, the halo's vast, uncharted reaches could shelter entire populations of them. Some models even suggest these objects could have formed before regular stars, in an era when the cosmos was a seething soup of exotic particles. Over billions of years, they'd have migrated to galactic halos, drawn by the same gravitational currents that sculpted galaxies themselves. The search hinges on indirect clues. If a dark star passed between Earth and a background star, its gravity would bend the distant star's light in a telltale flicker, an effect called gravitational microlensing. Astronomers have used this technique to spot rogue planets and even isolated black holes, but the signature of a dark star would be distinct, a lensing event without any visible counterpart. Other methods involve studying anomalies in the motion of globular clusters or gas clouds, their trajectories subtly perturbed by unseen masses. Yet the most tantalizing possibility isn't just finding one, it's what they could reveal about dark matter itself. If dark stars exist, their structure and distribution would expose the behavior of the particles composing them, offering the first direct glimpse into dark matter's elusive nature. Are these objects dense and compact like neutron stars, or diffuse and sprawling like ghostly fog banks? Do they evaporate over time, seeding halos with exotic radiation? Each question holds the potential to crack open one of cosmology's greatest mysteries. Of course, skepticism abounds. Some theorists argue dark stars are too unstable to persist for billions of years, collapsing into black holes or dissipating into the cosmic background. Others contend that even if they formed in the early universe, mergers and tidal forces would have ripped them apart long ago. But the mere possibility keeps the hunt alive, because if even one dark star hides in Andromeda's halo, it would rewrite our understanding of stellar evolution, dark matter, and the very fabric of reality. For now, these celestial phantoms remain just beyond our grasp, their existence hovering between theory and revelation. But the universe has a way of surprising us, and Andromeda's halo is the perfect stage for the unexpected. Whether as massive as a galaxy or faint as a whisper, the truth is out there, waiting in the dark. Frozen in time within Andromeda's halo, a ripple of light expands silently, an echo from a cataclysm that tore through the cosmos centuries before telescopes turned toward the stars. This isn't radiation from the explosion itself, but something far more haunting. Light that bounced off interstellar dust, delayed and stretched, reaching us only now like a whisper bouncing through cosmic halls. These light echoes are the universe's way of preserving its most violent moments, allowing us to witness supernova long after their fireballs have faded to embers. The physics behind these echoes is as elegant as it is eerie. When a star explodes, its light races outward in all directions at, well, the speed of light. Most of it streams straight to Earth, arriving in a flash visible for weeks. But some photons take a detour, striking vast clouds of dust lingering in the halo. These dust particles act like celestial mirrors, reflecting the light toward us years or even centuries later. The result, a glowing shell expanding outward at the speed of light, its surface etching the shape of the original explosion onto the sky. It's a hologram written in stardust, a delayed broadcast from a stellar death we thought had faded into history. What makes Andromeda's particular echo so remarkable is its clarity. Most light echoes are faint smudges, detectable only after painstaking analysis. but this one forms near-perfect concentric rings, like ripples from a stone dropped in a pond, each one marking a different layer of dust illuminated by the supernova's flash. By measuring the ring's expansion rate, astronomers have pinpointed the explosion to around the year 1650, ironically, just a few decades before humans built telescopes powerful enough to notice such an event. Had it occurred in our own galaxy, it might have outshone the full moon. Instead, its legacy hides in these ghostly reflections waiting to be decoded. The echoes aren't just pretty pictures, they're time capsules. Embedded in their light are spectral fingerprints of the elements forged in the supernova's heart: titanium, nickel, even traces of gold. These elements weren't present in the original star. They were born in the explosion's fury, cooked in a cauldron of unimaginable pressure and heat. By dissecting the echo's light, we're essentially performing an autopsy on a star that died before Newton published his laws of motion. But the real magic lies in what these echoes reveal about the halo itself. The dust clouds reflecting the light aren't random. They're the shredded remains of earlier stellar generations floating in vast, uncharted sheets. Mapping their positions through the echoes is like turning on a blacklight in a cosmic crime scene, exposing hidden structures we'd never see otherwise. Some appear aligned with streams of stars, suggesting they're debris from dwarf galaxies Andromeda consumed long ago. Others form puzzling geometries, hinting at magnetic fields or interstellar winds shaping the halo's invisible architecture. Perhaps most astonishing is what the echoes don't show. Supernova leave behind corpses, neutron stars, or black holes, yet no compact object lurks at the echo's center. Either the remnant is too faint to detect, or something even stranger happened here. Some theorists suggest the star might have collapsed directly into a black hole without the usual fireworks, leaving only the light that escaped before the final plunge as its memorial. This celestial feedback loop offers more than just a glimpse into the past. It's a living laboratory for studying how energy propagates through galactic halos, how dust clouds scatter light, and how the echoes of dead stars might influence the birth of new ones. Every photon bouncing off those distant dust grains carries a story not just of destruction, but of the intricate, invisible webs that bind galaxies together. And as the echo continues to expand, fading into the halo's darkness, it reminds us that in the cosmos, nothing ever truly vanishes. It just waits silently for us to listen. Tucked away in the sprawling expanse of Andromeda's halo, a tiny gem of light defies the darkness, a mini-halo, a compact, brilliant knot of stars and gas shining with unexpected intensity. This isn't just a random clump, it's a cosmic survivor, a dense pocket of matter that somehow resisted the tidal forces tearing apart everything around it. What makes this miniature marvel so fascinating isn't just its brightness. It's the lingering question of whether we're looking at the last, unbroken core of a galaxy long since consumed by Andromeda's hunger. Picture a galactic demolition derby. When a smaller galaxy plunges into a giant like Andromeda, it doesn't go quietly. Tidal forces, the same gravitational pull that creates ocean tides on Earth, stretch and shred the victim, peeling away stars and gas like layers of an onion. But deep within that chaos, sometimes the galaxy's heart holds firm. Its central region, packed with stars and anchored by dark matter, can remain intact even as its outer layers are stripped away, left to orbit as a solitary beacon in the halo. That's what some astronomers believe this mini-halo could be, the stubborn nucleus of a galaxy that refused to die completely. The evidence lies in its composition. Unlike the scattered, aging stars typical of halos, this cluster burns hot and young, its light tinged with the blue glow of recently formed stars. That's unusual for a galactic corpse unless, of course, it retained enough gas during its death throes to spark new stellar births long after its demise. Even more telling is its chemical makeup. The stars here are richer in heavier elements like iron and silicon than their halo neighbors, suggesting they formed in a denser, more evolved environment, exactly what you'd expect from a devoured galaxy's core. Yet there's a competing theory. This mini-halo might not be a survivor at all. Instead, it could be a rare stellar supercluster, a group of stars born in a single, explosive burst of star formation within the halo itself. Imagine a wandering cloud of gas, dense enough to collapse under its own gravity, igniting a firestorm of stellar births without ever being part of a larger galaxy. Such objects are rare but not impossible, and if true, this mini-halo would represent an entirely different chapter in Andromeda's story, one where the halo isn't just a graveyard but an unexpected nursery. The debate hinges on motion. If the stars in this knot move in unison, tracing the same orbital path like soldiers marching in formation, it's likely the remnant of a devoured dwarf galaxy. But if their movements are more chaotic, a jumble of orbits with no clear direction, it's probably a supercluster born in situ. Current observations lean toward the former. The stars here share a remarkably similar trajectory, as if bound by the memory of their original home. What makes this tiny island of light so much more than a curiosity is what it reveals about galactic evolution. If it's indeed a survivor, it's proof that even in destruction, galaxies leave behind fragments of their identity, cosmic fingerprints that outlast their dissolution. And if it's something else entirely, it challenges our assumptions about where and how stars can form, pushing the boundaries of what we thought possible in the so-called dead zones of galactic halos. Either way, this mini-halo is a time capsule. Its stars hold the answer to just how violent Andromeda's past truly was, and how much of that violence is still written in the sky, waiting to be read. Streaking through Andromeda's halo like a runaway lighthouse beam, a lone neutron star spins wildly, blasting jets of radiation into the void with clockwork precision. This isn't just any pulsar, it's a cosmic fugitive, hurling through space at nearly 1,000,000 miles per hour. Its path marked by a shimmering trail of radio waves stretching light years behind it. Most pulsars spend their lives anchored to the galactic disk, spinning predictably amid the stars where they were born. But this one, it's a renegade, fleeing its birthplace with a velocity so extreme, not even Andromeda's gravity can reel it back in. The secret to its escape lies in the violence of its creation. When a massive star collapses in a supernova, its core doesn't always explode symmetrically. Imagine a detonation so lopsided, the shockwave kicks the newborn neutron star like a cannon recoiling, launching it into space at breathtaking speed. That's likely what happened here. A stellar death throws so chaotic, it turned the corpse into a celestial bullet. But there's another, even more dramatic possibility. This pulsar might have been part of a binary system, orbiting a companion star until its partner went supernova first. The sudden loss of mass would have sent the surviving neutron star careening away like a slingshot released, its trajectory warped by the explosive farewell of its twin. What makes this pulsar extraordinary isn't just its speed. It's the wake it leaves behind. As it barrels through the halo, its powerful magnetic field interacts with sparse interstellar gas, generating a luminous shockwave visible in radio telescopes. This trail isn't static. It ripples and twists, mapping the pulsar's encounter with invisible density variations in the halo's structure. Think of it as a cosmic contrail, revealing turbulence in regions we once assumed were near empty. Yet the real intrigue lies in its isolation. Pulsars this fast are rare, and finding one so far from star-forming regions suggests it's been traveling for millions, possibly billions of years. Tracing its path backward leads astronomers not to a bustling stellar nursery, but to a quiet stretch of Andromeda's disk where its parent star likely died eons ago. That longevity raises a tantalizing question. How many more of these high-speed orphans are drifting unseen through the halo, their radio beams sweeping across space without ever crossing Earth's line of sight? Then there's the pulsar's rhythm. Most neutron stars slow predictably as they age, their spins gradually winding down like an unwinding toy top. But this one ticks with erratic precision, its pulses occasionally skipping or stuttering. Some researchers speculate it's grazing dense pockets of dark matter, its magnetic field momentarily disrupted by collisions with invisible particles. Others suggest it might be dragging a tiny, asteroid-sized companion, a cosmic hitchhiker picked up during its journey, now orbiting close enough to disturb its rotation. What's undeniable is the pulsar's defiance of expectations. It shouldn't be here in the halo's emptiness, blazing a trail where few stars dare to wander. Its very existence forces us to rethink how stellar corpses interact with their environments, how gravity shapes their fates, and how much energy the universe can channel into a single, speeding remnant. Every pulse of its beams carries data, a coded message about the forces that shaped it and the invisible structures it's traversing. As it continues its solitary flight, this wandering pulsar serves as a reminder that even in the quietest corners of a galaxy, motion never ceases. Whether it's a product of asymmetric explosions, gravitational betrayals, or some unseen interaction, its journey underscores a universal truth. In the cosmos, birth is only the beginning. The real story is written in the escape, threading through the depths of Andromeda's halo like an invisible umbilical cord. A river of pristine gas stretches far beyond the galaxy's visible edges, not just a local oddity, but a direct tether to the cosmic web, the universe's vast scaffolding of dark matter and primordial material. This filament, glowing faintly in ultraviolet light, isn't merely drifting. It's channeling raw fuel from the intergalactic void straight into Andromeda's star-forming factories, a lifeline woven during the universe's infancy and still pulsing with purpose today. To grasp the filament's significance, picture the cosmic web as a colossal network of highways, its intersections marked by galaxies and its lanes traced by streams of hydrogen gas left over from the Big Bang. Most galaxies, including our Milky Way, interact with these filaments indirectly drawing from reservoirs of nearby gas. But Andromeda's halo cradles something far more direct, a thread of the web itself, untouched by stellar explosions or galactic winds, its atoms as pristine as they were 13 billion years ago. Spectroscopy reveals its composition, hydrogen so pure it lacks even the faintest traces of heavier elements, a relic of the universe before stars polluted it with metals. This isn't just a passive strand of gas. Observations show it's flowing, its currents guided by the gravitational pull of Andromeda's dark matter halo. Like a conveyor belt feeding a furnace, the filament funnels material toward the galaxy's outer disk, where it condenses into clouds that will eventually collapse into new stars. The process is slow. Think of a trickle, not a flood, but over billions of years, this trickle has sustained Andromeda's growth, providing a steady diet of fuel untouched by the chaotic recycling of galactic centers. What's astounding is the filament's resilience. Simulations suggest it should have fractured long ago, shredded by tidal forces from passing galaxies or heated to invisibility by ultraviolet radiation from quasars. Yet here it is, intact, its structure preserved by some combination of dark matter's grip and the halo's relative quiet. Some researchers speculate it's shielded by magnetic fields, their invisible lines wrapping the gas like a cocoon. Others propose it's simply too diffused to disrupt, its atoms too sparse for even gravity to fully dismantle. The filament's existence forces us to rethink how galaxies evolve. We've long assumed that massive spirals like Andromeda grow primarily by swallowing smaller galaxies, a violent, haphazard process. But this cosmic thread suggests another, gentler mechanism, continuous feeding from the web, a slow infusion of virgin gas that keeps the galaxy's star-forming engines humming without the drama of collisions. It's a reminder that the universe doesn't just build galaxies through chaos, it nourishes them with whispers, and the implications stretch beyond Andromeda. If similar filaments thread other galactic halos, they could explain why some galaxies keep forming stars long after their peers have faded into retirement. They might even hold clues to the universe's missing baryons the ordinary matter theorists predict should exist but can't account for. Perhaps these faint, flowing strands are the universe's hidden aqueducts, their contents too diffused to see but vital to the cosmic ecosystem. As telescopes grow more sensitive, they'll trace this filament's path deeper into intergalactic space, mapping its connections to the web's grand architecture. Each new observation peels back another layer, revealing how the universe's largest structures whisper to its smallest. For now, this river of primordial gas remains a silent architect of Andromeda's destiny, proof that even in the darkest voids, the universe never stops giving. Amid the sparse wilderness of Andromeda's halo, a fiery constellation blazes against the darkness, a swarm of red giants, each burning with the slow, stubborn intensity of stellar old age. These aren't the delicate, newborn stars of the galactic disk. They're cosmic elders, massive stars that have exhausted their hydrogen fuel and now swell into monstrous sizes, their outer layers cooling into the crimson glow that gives them their name. What makes this gathering extraordinary isn't just their numbers. It's how these dying stars serve as lighthouses, illuminating the invisible architecture of the halo itself. Red giants are nature's perfect tracers. Their sheer luminosity, up to thousands of times brighter than our sun, makes them visible across staggering distances, even in the halo's outermost reaches where most stars fade into obscurity. But their true value lies in their predictability. Unlike younger stars, which vary wildly in brightness, red giants follow well-understood evolutionary paths. By measuring their precise colors and intensities, astronomers can calculate their distances with remarkable accuracy, turning each one into a signpost marking its location in three-dimensional space. This swarm's arrangement tells a story of gravitational drama. Instead of clustering neatly around Andromeda's core, the red giants form intricate, looping patterns, some grouped in tight knots, others strung along vast arcs like beads on a celestial necklace. These aren't random distributions, they're scars from ancient mergers, the stellar remains of dwarf galaxies torn apart by Andromeda's gravity billions of years ago. Each clump corresponds to a different victim, their stars now assimilated into the halo but still clinging to the memory of their original orbits. The real breakthrough comes from combining these observations with motion studies. By tracking how the red giants drift over time, a painstaking process requiring years of telescope data, researchers can map the halo's gravitational field in unprecedented detail. Some stars move faster than expected, hinting at unseen concentrations of dark matter tugging at them. Others trace odd corkscrew paths, suggesting the halo isn't the smooth, featureless sphere we once imagined, but a lumpy, dynamic structure shaped by countless collisions. Here's where the giants reveal their greatest secret, their chemistry. While most halo stars are metal-poor, born before heavy elements were common, some of these red giants contain surprising traces of elements like carbon and barium. These anomalies suggest they were forged in later generations, perhaps in dwarf galaxies that managed to brew a few rounds of stars before being consumed. It's a subtle detail, but one that lets astronomers reconstruct not just where these stars came from, but when they were swallowed, adding chapters to Andromeda's growth timeline. Beyond their scientific utility, the red giant swarm offers a poetic glimpse into stellar mortality. Each of these crimson behemoths is a star in its final act, having spent millions of years fusing heavier elements in its core. Soon they'll shed their outer layers entirely, leaving behind dense, Earth-sized embers called white dwarfs. For now, though, they burn as beacons, their light cutting through the halo's darkness not just as relics of destruction, but as guides to the hidden forces that shape galaxies. Their collective glow is more than a cosmic spectacle, it's a language. By deciphering its patterns, we're learning to read the halo like a history book, one where every star holds a sentence, every cluster a paragraph, and every stream a chapter in Andromeda's epic of growth and transformation. And as telescopes grow sharper, the story will only deepen, revealing connections we've yet to imagine between the living and the dead, the seen and the unseen, in this grand celestial dance. Stretching into the halo like a ghostly afterthought, a faint but unmistakable spiral arm drifts far beyond Andromeda's luminous disk, an ethereal extension where no spiral arm should exist. This phantom limb, barely visible against the darkness, curves gracefully through the halo's emptiness, its stars sparser and older than those in the galaxy's bustling main arms. At first glance, it seems impossible. Spiral arms are delicate structures, reliant on the dense gas and orderly rotation of a galactic disk to maintain their shape. So how did this one escape into the void, untethered from the forces that birthed it? The answer lies in Andromeda's violent past. Simulations reveal this structure as a cosmic scar, the lingering imprint of a near-miss collision with another galaxy billions of years ago. Picture two galaxies passing close enough to disrupt each other's shapes but not quite merging. As the intruder grazed Andromeda's disk, its gravity tugged vast streams of stars and gas outward, stretching one of the spiral arms like taffy. Most of the displaced material eventually fell back into the disk or scattered into the halo, but this arm held together, its stars bound by their shared momentum. Over eons, the galaxy's rotation twisted the structure into its current eerie pose, a frozen wave breaking silently in the cosmic dark. What makes this phantom arm extraordinary is its defiance of decay. Normally, such delicate features would dissolve within a few 100 million years, their stars dispersing into the halo's chaos. Yet here it persists, a testament to the precision of the initial encounter. Detailed simulations suggest the colliding galaxy must have struck at just the right angle and speed, a gravitational brushstroke so perfect it left behind a structure that's neither fully part of Andromeda nor entirely separate. The arm's very existence pins down the timeline of that ancient encounter, offering clues about the intruder's size and trajectory, but the real revelation lies in the arm's stellar population. Unlike Andromeda's vibrant disk, where young blue stars dominate, this structure is filled with aging red giants and white dwarf stars that were already ancient when the collision occurred. Their chemistry matches the galaxy's inner regions, confirming they were ripped from the disk rather than being absorbed from another galaxy. It's as if the arm is a snapshot of Andromeda's disk frozen in time, preserving a piece of the galaxy as it looked before the encounter reshaped everything else. Mapping the arm's faint glow has required telescopes capable of detecting the subtlest starlight, but the effort reveals hidden layers of the halo's structure. The arm's path aligns with several star streams and globular clusters, suggesting it might be part of a larger, invisible current of debris, a river of stars winding through the halo, marking the intruder's path like breadcrumbs. Some researchers even speculate the arm could be feeding material back into Andromeda's disk, its outermost stars gradually returning home like salmon swimming upstream. This celestial fossil does more than recount an ancient collision. It challenges our assumptions about galactic resilience. Spiral arms aren't just transient features. Under the right conditions, they can become cosmic survivors, outliving the events that birthed them. As telescopes peer deeper, they may uncover more of these ghostly limbs in other galaxies, each one a silent witness to the encounters that shape the universe. For now, this phantom arm remains a reminder that even the grandest structures are born from chaos, and that violence, when sculpted by time, can create unexpected beauty. Deep in the cosmic shadows of Andromeda's halo, an invisible giant lurks, an object with the gravitational pull of a small galaxy but none of the light. This enigma, known as a dark galaxy candidate, weighs as much as 10 billion suns, yet when astronomers point their telescopes at its coordinates, they find nothing. No stars, no glowing gas, just an expanse of perfect darkness bending the fabric of space around it. The evidence for this phantom comes from its gravitational grip. Nearby star streams bend sharply as they pass through the region, their trajectories warped as if caught in an invisible whirlpool. Dwarf galaxies orbiting Andromeda slow inexplicably when they approach this patch of sky, their motions betraying the presence of something massive we cannot see. The math is clear. There's matter here, lots of it arranged in a stable, galaxy-sized structure. But the light we'd expect from even the dimmest dwarf galaxy is entirely absent. This absence sparks fierce debate. One camp argues we've finally found a true dark galaxy, a clump of primordial gas and dark matter that somehow avoided forming stars altogether. Picture a failed cosmic experiment, a pocket of the early universe where matter clustered under gravity but never ignited into stellar fire. Such objects were predicted by theories suggesting dark matter halos could exist independently, their gas too diffuse or too undisturbed by shocks to collapse into stars. If confirmed, this would be the first incontrovertible proof that the universe harbors galaxies built entirely from the unseen, but skeptics raise compelling counterarguments. Could the gravitational anomalies stem from a chance alignment of multiple smaller dark matter clumps, or an error in modeling Andromeda's complex halo? Even the tiniest miscalculation in star velocities could exaggerate the apparent mass of this region. Some propose it's not a single object at all, but the accumulated pull of hundreds of rogue black hole stellar remnants flung into the halo during galactic collisions, now clustering like invisible buoys in a dark sea. The most tantalizing clue comes from subtle distortions in the cosmic microwave background, the afterglow of the Big Bang. Some models suggest the dark galaxy candidate's location aligns with a slight cold spot in this radiation, a fingerprint possibly left by a massive, lightless object warping spacetime across billions of years. Yet even this evidence remains contentious, with alternate explanations like cosmic voids or statistical noise muddying the waters. What's at stake isn't just the identity of one odd object, but our understanding of galaxy formation itself. If dark galaxies exist, they could solve the missing satellites problem, the puzzling shortage of small galaxies orbiting large ones compared to cosmological predictions. Perhaps the missing galaxies were dark all along. Alternatively, if this candidate dissolves under scrutiny, it forces us to reconsider how we map the invisible scaffolding of the universe, reminding us that even our best tools have limits. For now, the dark galaxy candidate lingers in scientific limbo, a gravitational whisper without a face. Every new observation sharpens the puzzle without solving it, a testament to how much of the cosmos remains hidden in plain sight. Whether it's a landmark discovery or a cosmic mirage, its very existence challenges us to rethink what we mean by the word galaxy, and how much of the universe might be playing hide and seek in the dark. At the farthest fringe of Andromeda's halo, where the galaxy's gravitational grip grows weak, something extraordinary happens. The boundary between here and there dissolves into cosmic ambiguity. This outermost edge isn't a sharp border, but a gradual fading like ink diffusing in water, where the last outposts of Andromeda's influence mingle with the void of intergalactic space. Here, stars become so sparse that traveling through this region would feel like crossing an endless ocean under a night sky where the brightest landmarks have all but vanished. What defines this transitional zone isn't just distance, it's a shift in the rules of engagement. Within the inner halo, stars and gas move in orderly orbits, bound by Andromeda's persistent pull. But at the outer edge, the galaxy's gravity is so feeble that passing dwarf galaxies or the tug of neighboring galaxy clusters can yank material away entirely. Some stars here aren't even truly Andromedas, they're intergalactic wanderers, drifting between galaxies like cosmic nomads, briefly captured before continuing their endless journey through the abyss. The halo's outer reaches are also a graveyard for galactic encounters, When Andromeda collided with smaller galaxies over billions of years, the violence didn't just scatter stars, it ejected some entirely, flinging them into orbits so wide they barely cling to the galaxy at all. These extreme trajectories create a fuzz of stars stretching millions of light years, a ghostly afterimage of ancient mergers that simulations suggest might even overlap with our own Milky Way's outermost stars. Yet the most fascinating feature of this frontier isn't stars, it's gas. Vast, wispy clouds of hydrogen linger here, so diffuse they'd barely register if you flew through them, yet collectively massive enough to fuel future generations of stars. Some are remnants of Andromeda's birth, pristine reservoirs untouched by stellar explosions. Others might be intergalactic hitchhikers drawn in from the surrounding cosmic web. Unlike the inner halo's turbulent history, this gas drifts almost undisturbed, a relic of quieter times before galaxies grew large enough to dominate their surroundings. This boundary region also holds clues to Andromeda's ultimate fate. As the galaxy hurtles toward a collision with the Milky Way, the outer halo is the first to interact, a vast, invisible handshake of dark matter and tenuous gas that will shape how the two spirals merge. Long before their stars begin to mingle, these outermost tendrils will intertwine, a prelude written in the faintest whispers of matter. Standing at this edge, we see Andromeda not as an island, but as a living system breathing in the currents of the cosmos, forever growing, forever changing, its boundaries as fluid as the universe itself. The halo's outer limit isn't an ending, it's a threshold where one galaxy's story bleeds into the next. From ghostly hydrogen clouds to rogue black holes, from phantom galaxies to glowing filaments of ionized gas, these 30 strange objects paint a portrait of Andromeda unlike anything we imagined. Each one is a clue, a cosmic breadcrumb leading us through the galaxy's turbulent past of collisions, cannibalism, and chaos. The halo isn't just a graveyard of ancient mergers, it's a living record whispering secrets about how galaxies grow, evolve, and sometimes defy the rules entirely. Think about it, that invisible dark matter clump warping orbits, the hypervelocity star racing toward intergalactic exile. Even the binary quasars locked in their deadly dance, they're not just oddities. They're proof that the universe reserves its most astonishing creativity for the places we least expect. What's truly humbling is how much remains unanswered. That gamma-ray glow, could it really be dark matter annihilating itself, or is it something even stranger? The tidal dwarf galaxy forming new stars in the halo's darkness, how many more of these cosmic phoenixes are out there? And that eerie infrared ghost radiating heat with no visible source, what undiscovered phenomena might it represent? Every mystery we've uncovered in Andromeda's halo suggests a dozen more waiting in the shadows, not just here but in the halos of galaxies across the cosmos. So here's the thrilling part, this isn't the end, it's an invitation to look up at Andromeda, that faint smudge in the night sky, and see it for what it truly is, a dynamic, ever-changing island of stars with a halo teeming with enigmas. What do you think lurks out there? A new class of object we haven't even named yet, evidence of physics beyond our current understanding, or perhaps something so bizarre it'll rewrite our cosmic playbook entirely. The universe loves surprises, and if Andromeda's halo has taught us anything, it's that the best discoveries often come from the places we thought were empty. If unraveling cosmic mysteries like these excites you, you're in the right place. Hit subscribe to join us as we keep exploring the universe's greatest puzzles, because the next big revelation might be hiding in plain sight, just waiting for someone to look closer. And hey, drop your wildest theories in the comments. Who knows, your idea might just be the key to unlocking the next galactic secret. Until then, keep wondering, keep questioning, and remember, the universe's greatest stories are always written in the dark.